Okay, today I start chapter 9, 1 and 2 sample estimation. So what is it? We have some distribution, say, and this distribution has maybe one or more than one parameter. So we are assuming that we know the distribution. So we just take it to be, say, normal or something else. And it has parameter or parameters. Now let's say it has just one. Or even if it has more than one, we go one by one, or sometimes we take into account both of them. Well, so let's say that we want to estimate this theta, the parameter. Now, let me say, for example, for a normal distribution, we have mu and sigma squared. Like we will estimate mu, assuming that we know sigma squared, and sometimes we don't know sigma squared, but anyway. So that's what I mean by theta, parameters. So those are parameters of the normal distribution. Now, we will start with what is like, it's called the classical method. In classical method, we define like a point estimate for the parameter, and then take a sample of size n or something, and then study that sample, find the x bar and sigma s squared and blah blah blah, and then find a nice estimate for theta. Now, the one that I discussed today is called the confidence interval. Okay, so let's say we have an estimator. So estimator, well, let's call it theta, big theta, capital theta or something. And we want this estimator to be unbiased. So this estimator theta estimates small theta. Unbiased estimator. So we say theta is unbiased if the expected value of this equals theta. Okay, so we, in fact, in the previous chapter, we found estimators. We found the distribution for those estimators. And so let's write down the two estimators, basic estimators that we used for normal distribution, and see if they are biased or not, or they are unbiased, in fact. Okay, so let me erase this and look at those two estimators. So for mu, we had x bar n, which is 1 over n sigma I from 1 to n xi. And that comes from a sample x1 up to xn. So we just suppress that. We take sample of size n, and then we find x bar of that sample. Let's see if this equals mu. So E of x bar. Now, first of all, again, I should mention that these xi's, all of them are the copies of the x of the population distribution, because we are taking the sample from the population. So each one of them is like the distribution of the population. It has the distribution of the population, so it has the same parameters. So each xi is the same as x, and x was normal with mu and sigma squared, right? So E of xi is mu, and variation of xi is sigma squared for all I. Okay? And I also mentioned that because these are all random variables, the sum of them divided by some constant is also a random variable. So this x bar n, which is a function of some random variables, is in fact a random variable. So this makes sense. Okay, so that is E of 1 over n sigma xi I from 1 to n. We know that this constant comes out, and we have sigma. The sigma also comes out. E of xi I from 1 to n, and that is in fact 1 over n. Each one of them is mu. We have n of them times n mu, which is mu. So x bar is unbiased. Unbiased. Estimate of mu. Now, before I try the other one and find out whether S squared is also unbiased, let me give you some idea of what's going on. Okay, this estimator we found. Let me erase this thing. Let's see what happens if, in fact, what we put. So we showed that E of x, we knew this thing anyway, but this is mu. So if x bar has some distribution, we know the distribution of x bar, that is normal with mu and sigma squared over n. Now, this means that if mu is here on the x-axis, then x bar is like this. So this is unbiased. But if I have a distribution for some, not mu, something else, and the distribution looks like this, say, and it's, say, expected value is somewhere here, then that's not unbiased, that's biased. So that's what, at least in picture, this means. Okay, so unbiased estimators, the distribution of unbiased estimators are in fact concentrated here. Or no, not concentrated, but the mean is here. Okay. Let's take the other one, S squared. Let me erase this, and S squared was 1 over minus 1 sigma xi minus x bar n. Okay, so this one is a little tricky, and it's interesting that you will see in the end why. No. So we have to use the following identity. That identity is, we had it in the past, xi minus x bar n, I'm not going to put it again, and that is sigma mu squared minus n times x bar n minus mu. Okay, so E of S squared will be E of Well, I have 1 over n minus 1, so 1 over n minus 1 comes out, and I have sigma I from 1 to n e of this thing xi minus mu squared, and minus n e of x bar n minus mu squared. Okay? So, let's look at each one of them. So, e of xi minus mu squared, that by definition is sigma I squared, right? But that's in fact what I'm doing. By definition is variance of xi, and that is sigma squared. And the other one is in fact e of, remember, x bar n has distribution normal with mu and sigma squared over n, mu as mean. Now what is it? What if you subtract this from its mean, square it, this is in fact the variance of x bar n. So that's sigma squared over n. Okay? So let's just plug in everything here. This. So if I plug in, I have e of s squared 1 over n minus 1. Here I have sigma squared and n sigma squared because I have n of them minus n times sigma squared over n. So that's 1 over n minus 1. And this is sigma squared. N sigma squared, that's n minus 1 sigma squared. So that is sigma squared. And you see why we need n minus 1 here. If I had n over there, then I would get n minus 1 over n. Then that was not biased. And that was not unbiased. That was biased, in fact. Okay, so the two estimators, x bar n, which estimates mu, and s squared, which estimates sigma squared, are in fact unbiased estimators for these two. Okay, now let's start. Okay. Now, interval estimation. Interval estimation intuitively means that you want to estimate, say, mu, for example, and then you find an interval such that mu falls in that interval with some good probability. So you say with probability of 0.9, for example, 90%, mu falls between these two numbers. That's basically what interval estimation is. That's what the end result is. You give the person who is asking for it an interval and say that mu for the average, say, or whatever, it falls within this interval with 90%, 95% confidence. That's what the terminology used for that. So let's see. Well, I have given a nice discussion in the notes on this, but what it means is this. So we want this. So we are estimating theta. So we find two random variables. Theta L and theta U, such that guess I have usually used a hat for them because these are some kind of estimator. So these are the two random variables which in fact give me the two endpoints of the confidence interval. So we want this to be 1 minus some alpha. And alpha is in fact a probability. So that's between 0 and 1. So this statement is ambiguous. In fact, you might say, okay, well, what are we talking about? We are talking about two random variables which we don't know what they are, and that alpha is given. That alpha is given. That's so 1 minus alpha is given, and theta is unknown. We want to find it, or to estimate it, say. In a sense, this is like a statement on these two, or the joint distribution of theta L and theta U. But what happens is, in practice, when I will start doing one sample, and you will see what they are. They are like random variables related to the theta, to the estimator somehow, or part of the estimator. So we use that estimator for the little theta to find these two. So it's better to give you examples, and then you will see for yourself that the two ends are in fact random variables. Okay, so let's start with estimating so the first type is single sample estimating mean sigma squared. Okay, so sample of size n. So we have a sample of size n, and so what do we know? So let's start with that estimator. What is the estimator for mu? Estimator for mu is that x bar. And we know that this guy here is in fact normal with mu and the sigma squared over n, assuming that the sample is from a normal distribution. So it's from normal distribution, normal mu and sigma squared. Okay, we know this from the previous chapter. So what else do we know? We also know that Zn, which is x bar of n minus mu over sigma over root of n, this approaches a z which is normal 0. This also we know. Okay. So now, given alpha, so alpha is a number between 0 and 1, right? Alpha is a number between 0 and 1, and we do this. We find 2 points. Well, let me, n01 is this, say, so that's n01. And we find 2 points here and here. This one is minus z, we call it alpha over 2. And this one is z of alpha over 2. So these are the points. These are the points for which for example, on this side, probability that z is bigger than z alpha over 2 is in fact alpha over 2. And the same on the other side, when z is less than minus z alpha over 2 is alpha over 2. So what's the probability that z is between these two? Here. So P of z between z of alpha over 2 and minus z alpha over 2 will be, so that's alpha over 2, add them, it's alpha, so that's 1 minus alpha. So if I choose these two, then I will get 1 minus alpha. Now, well, let's do it. Let's well, up to this point, you might say, what are we doing? Well, wait, you will see. So this z over there, the zn, in fact, approaches z. So I can say that this zn is, in fact, as n gets larger and larger, is normal 0, 1. So let's just write zn here. X bar n minus mu sigma over square root of n. And let's write minus z alpha over 2, and this is a number, z alpha over 2. Okay? And we know that this is approximately, not exactly, because this one is not exactly normal 0, 1. But as n gets larger and larger, we can just say, okay, this is 1 minus alpha. Okay? So, but let's simplify this. I need something which is mu in the middle. So what should I do? First I multiply inside, and remember, when I write this equal to something, another probability, it means that I am doing something inside, some algebraic manipulation that can be reversed. So if I can reverse the algebraic manipulation, then the two probabilities are the same. So first I multiply both sides, all three sides, by sigma over square root of n. That can be reversed. Then I will find mu. So it's like subtracting this one from this side and this side, and then reversing the sign, because then that's minus mu, and I will get this. So mu will be in the middle, and on this side I have x bar of x bar n plus sigma over square root of n z alpha over 2, and on this side I have x bar n minus sigma over square root of n z alpha over 2, and this equals 1 minus alpha. Okay. So, well, I said, well, this is like a theta, so this is what I'm estimating, and you see that I have written a statement probability of this guy here in the middle, bigger than, less than, and this one is that theta at low. You see that is a random variable. X bar n is a random variable, or it's minus something. And this also is theta u. Okay? So we have achieved that goal. We have found like an expression with the thing that we are estimating in the middle, and two random variables on the two sides, and that probability equals 1 minus alpha. So we have achieved what we want. Now, what does this mean? Because these are random variables. So what is the... Now, this means that if... So I have a random sample, right? Random sample on one hand means that I have like n random variables. On the other hand, in practice, you find values for those random samples. So the random samples, the xi's, they take values. And that's what you do in practice. So you go out there and as people, well, if you're studying something like the age of people, so that is the random sample. And then you find that x bar n, a value for x bar n, right? So if x bar, let's just write x bar, is the value taken by x bar n, then we can say this. We can say the mu lies in this interval x bar minus, well, usually we write this one first, sigma over root of n, comma, x bar plus z alpha over 2, sigma over root of n, with probability 1 minus alpha, or with 100 times 1 minus alpha percent confidence. Okay, so that's the same thing. In fact, this is the terminology used because we talk about confidence interval. Okay, so you go out there and find n samples. I mean, it means that you find values for those xi's, in a sense, or you assign values to those xi's, and then find x bar n, and that x bar n, the value of that x bar n is this small x bar here, and so this means that if I find x bar, then mu lies in this interval with probability 1 minus alpha. Now, what does this mean? If you go out there and do that and give me some interval, what does it mean? So if you, let me erase this, and that's also crucial, understanding this side of the story. So you find something, you say, okay, I have found that mu is between 1.07, say, and 1.09, say, with 100 times 1 minus alpha percent confidence. So if I say alpha is 0.05, that's one of, usually you take it 0.05 or maybe 0.01, depends. So this gives me 100 times 1 minus alpha, that's 95, so that's 95% confidence. Or probability 0.95. So what does this mean? 95% or 0.95. So you have done an experiment. So you go out there, take n samples, and find x bar, and you find these two numbers, 107, 109, and then you make such a statement. You say this. So just look, one experiment, a probability of success. It means that, in a sense, it means that if it falls in this, you are successful. So what is the probability of being successful? It's 0.95. So it reminds of Bernoulli process. So each one of them is like a Bernoulli process with a success probability of 0.95, 1 minus alpha. So that 1 minus alpha is in fact the probability of success. Or you can say it means that if I do this experiment 100 times, then in average, 95 times average, the mu falls within the interval, in average. This doesn't mean that if you do it one time, it definitely falls within this interval. No. So you are giving me a probability, which is good in fact. Now, why you do it one time? Well, it's not feasible. Maybe the experiment is expensive, or we can't do it 100 times or 10 times or even 2 times. So you just can do it one time, and then you just give me these two numbers as and this interval, and you say I have 95%. I'm 95% confident that it falls within this interval. So there are problems like this. So it's like saying we do an experiment, say 10 times, and we find the confidence intervals for each one of them. What is the probability that, say, 8 times out of 10, mu falls within the confidence interval of that specific experiment? So that is in fact binomial. So when it comes down to questions like this, then it is in fact a binomial distribution. So if you do the experiment, say, how many times? Say m times, so it will be do the experiment say m times, but n is that thing, m times, then say y is a success, say, then y has binomial distribution for m with p equals 1 minus alpha. So if you see problems like that, or well, in real life it might happen, so you ask a question like that we have done this experiment 100 times, but what is the probability that, say, 50 times we had mu within the confidence interval? So that's binomial. Okay. Now, what do you think happens if I do not assume that sigma squared is given? So one sample, so I have one sample again, estimating mu, sigma squared unknown. So remember what I used here was, what was the estimator for mu? Well, estimator was like z, again I can call it n. Estimator was x bar n minus mu divided by s squared over s over square, right? So, and that was the distribution of this thing was t n minus 1. Okay? So the distribution of this thing was t n minus 1. As n, don't mean n. So that is t n minus 1. So in this case, we need, so given 1 minus alpha, so we need this t alpha over 2 and minus t alpha over 2. Okay? So these two, the probability here is alpha over 2, and the probability here is also alpha over 2, and here is 1 minus alpha. So the probability that z falls within these two is 1 minus alpha. So let's write it. So p of this z falls within this. Right? Well, again, I simplify this thing and I find if on this side I have x bar n minus t alpha over 2 times s over square of n less than mu bigger than less than x bar n again plus t alpha over 2 s over square of n. So it's very similar to the other one, except the distribution of the estimator is the t distribution, not normal distribution. So we get the same, no, similar, except we have t distribution and we should calculate s. So So this is the estimator, this is the process, and this is what we get. And this means that mu falls within this interval, which is very similar to the other one. Sorry, this is another exponent. This is in fact the value x bar, and x bar is value taken by x bar. Sorry. Okay. So and or if again we can say that is 100 times 1 minus alpha %. Okay. So we have the two cases, sigma known and sigma unknown. For sigma known, we use normal distribution. For sigma unknown, we use t distribution with n-1 degrees of freedom. And I have given you examples using R in the notes, and you can start using R and find confidence intervals for different distributions. Real life problems anyway. So let's see. Now next is in fact there are also the two theorems on sample size and the error, which you can read from the notes. In fact, sample size means that you can ask this question: what sample size will give me a certain confidence interval with, say, 95% confidence or something like that. So sample size is this n. So you calculate n. There is this. You can find that if n is larger than this number, then you definitely will get a confidence interval with 0.95% probability. So let's go to two samples. And then check something. Okay. Two samples. And estimating mu1 minus mu2, say mu1 minus mu2, sigma square. So we have two distributions, in fact. So we have two distributions, and and we have two random samples. So one of them is x, what should I call that? X something. Well, so two random samples, x, I and y, whatever, and so it is 1, 2, x, and 1, say, and this is taken from some x, which is normal with mu1 and sigma squared 1. And the second one is taken from an x, which is normal with mu2 and sigma 2 squared. So these are two different. And what we want to find is the difference, estimate, I'm sorry, finding a confidence interval for the difference between the two mu's. Now, you can ask this question, okay, is mu1 minus mu2 close to say 0.01. Sometimes you really need that. You want to see if the two averages are close enough from two populations. Say age, for example. You want to see the age of this population in this city and the other city are close enough by taking, say, some samples from the two cities. And if the cities are far enough, you can say that they're independent. So the population distribution of whatever the age in that population, the two populations, we can assume that they are independent. So you can assume they have different mu's and different sigmas. Anyway, so that's one example. Comparing the age of two, average age of two populations into different cities, say. So we have this thing, and what did we find? So what was the estimator? Well, I guess I called this N1 and N2. So one of them has N1 samples, the first one, and the other one N2 samples, and we found that X bar N1 minus X bar N2 minus mu1 minus mu2, in fact, divided by what? Divided by this, sigma 1 squared over n plus sigma 2 squared over n. And that approaches z, which is 0, 1. In fact, what I found was that this xn1 minus xn2, both of them are normal, with mu1, mu2 as means, and when I subtract them, I will get another random variable. So this is a random variable which is normal, and its average is this, or its mean is this, and this is its square root of variance. So again, by CLT, it approaches some z which is normal 0, 1. Okay, so this is not anything new, except you have to remember that adding or subtracting normal distributions, normal random variables which have normal distribution will give you another normal distribution. So that was the thing behind the CLT and other things. So anyway, so we use the same thing. So we say, okay, if this is a z, and because sigma squared is known, we use n0, 1. So again, we have z alpha over 2 and minus z alpha over 2. This area between them has probability 1 minus alpha, so that gives me probability of 1 minus alpha. So p of minus z alpha over 2 less than this guy here. Let me not write it. It's z alpha over 2. This is 1 minus alpha. Okay? So just write this here. Now again, I solve for mu1 minus mu2. That's what I'm estimating. So I'll just do some algebraic manipulations, and I end up with this. So the end result is this. Probability of, on this side again, this will be x bar n1 minus x bar n2 minus sigma. Sorry, let's see z first. Z alpha over 2 times this square root sigma 1 squared over n plus sigma 2 squared over n less than mu1 minus mu2 and less than the same thing x bar n1 x bar n2 plus z alpha over 2 square root of this thing. This is 1 minus alpha. This is 1 minus alpha. So I can say that with confidence 100 times 1 minus alpha percent, mu1 minus mu2 falls within this interval. So let me write down the interval. And So mu1 minus mu2 all within this interval, except we are finding values for these two. So values taken by these two, and that's like x bar 1 minus x bar 2 minus t alpha over 2 times sigma 1 squared over n plus sigma 2 squared over n mu1 minus mu2 less than this. Okay. Also, comma x bar 1 minus x bar 2 plus. And that's n1, n2, so I forgot the n1, n2. They are different. N1. Okay, so with probability okay, so that is okay. Now the case that sigma is unknown, sigma squared unknown, is a little different, and I have written it in the notes. And in that case, it is t distribution with certain, say, degree of freedom, and the degree of freedom is like a big expression itself. Now, how does this happen? Why? Well, we need more knowledge of statistics to find that degree of freedom. In fact, like that degree of freedom, that formula gives you decimal number. So you have to find the floor of that, which is the lowest or smallest integer below that number. So I can write this for you, and just to mention that sigma squares unknown, and not just unknown, and they're different. So unequal. Well, it makes sense. So when you're dealing with two populations in two different cities, why should they have the same standard deviation? Or so what you do when you find the standard deviation, S, the sample standard deviation, you don't expect them to be the same. So this will give me something like this. So mu1 minus mu2 will be exactly the same up to this point. Then I have t alpha over 2, same, except here I have s squared over n1 plus s squared over n2, and x1, x12 plus t alpha over 2, and s2 over n1, oh, let's say this is s1 and s1, s2, 2 over n2. So that's the confidence interval. And the t distribution we use, so t alpha over 2 comes from the t distribution with nu, and this nu, in fact, is some big expression. So I'm not going to write it down. It's like so long. So it is something up here, something up here. It has to do with S and N. So, but when you find this nu, in fact, you don't write nu here. You write floor. So in fact, this should be T of floor. And the floor means floor of say 2.56 is 2. I guess you know what I'm talking about. So that is floor function. But anyway, this is perhaps the most, I mean, I can say that this usually happens. So this is the most general example. Okay, so I guess that's it. And there is, in fact, in this chapter some estimating S-squared in itself. You can read that for yourself. That's estimating standard deviation. Remember, there was n minus 1 S-squared over sigma squared. That was for standard deviation. You can read that. When you know the process, if you write it down and then find that sigma squared, in fact, and you can just find it easily. So I leave that to you, and that was, in fact, chapter 9. Okay, so see you next time.